Recording. Oops. I shared the wrong screen. Here we go. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. Okay, so today we're going to go on and take a look at section 11.5, the first part of it. But before we do that, I have several questions from students. And this is from section 11.4, number 8. It says, write the logarithm equation as an exponential equation. And the logarithmic, the logarithm equation is log of 0.01 equals -2. Now, there's no base written. The implied base is a 10. So there's a 10 down here. So putting this as an exponential equation, it would be 10 to the -2 power equals 0.01. Any questions about that? All right, we're going to take a look at problem number 41 now. It says, if P dollars is invested at the end of each year in an annuity earning annual interest at a rate R, the amount in the account will be A dollars after N years, where, and the formula looks like this, N equals the log of, let's see, AR over P plus 1 in the numerator and the log of 1 plus R in the denominator. Now, let's see. We are looking to find N, and we need to know what A is, and R is, and P is. Let's see here. If $1,000 is invested each year in an annuity earning 12% annual interest, how long will it take for the account to be worth $25,000? So A is the total amount in the account after N years. So that's going to be the $25,000. R is the annual interest rate, which is 12%, or as a decimal, 0.12. P is, let's see here, it's the amount invested, and that is $1,000. So basically, we start out by putting $1,000 in each year. How long will it take us to get $25,000 in the account? Okay, so N equals, in the numerator, we have the log of A, which is 25,000, times R, which is 0.12, all over P, which is 1,000, plus 1. And that's all over the log of 1 plus 0.12. Now, this is another case of where we can put everything into the calculator just as it is, or we can simplify it first. Let's see. I'm going to go ahead and simplify it first. So in the numerator, I've got 25,000. Let's see, put on my glasses here. 25,000 times 0.12 divided by 1,000, which is 3 plus 1 equals 4. Do you have any questions? Do you want me to go over that in any detail? Okay, so I got 4. On the bottom, 1 plus 0.12 would be 1.12. So now I'm going to take the log of 4 divided by the log of 1.12. And when I do that, I get 12.23251075. And that is years.
Sorry to interrupt you, but I'm not sure if you got the answer wrong, but I did the calculations for 25,000 times 0.12 divided by 1,000, and I got 3.
Yes.
And you got 4.
No, I got 3 plus
you
1.
added 1. Okay.
Yeah.
I see.
Okay. No, that's all right. That's all right. Keep me honest here. Okay. Now it says round your answer to 1 decimal place. So we would round here. The 3 would round down. So we get 12.2 years. All righty. Any questions on that? A lot of calculations there. Calculations.
I'm sorry, but
yeah.
I kind of got a little lost when I was explaining, but how did you get from log 4 divided by log 1.12?
How did I get to that or from that?
To that. Or actually from that. Or how did you get the answer is basically what I'm asking.
Okay. So you're okay to there?
Yeah, I'm fine with that part.
So in your calculator, you're going to put in log base 10, which is going to give you that. Then you're going to put in a 4. Then you're going to close it up. And then divided by log base 10, which is going to give you that. Then put in 1.12, close it up. But you've got to put that second set of parentheses there, or it thinks the whole thing is the first log. So try that.
Oh, okay. See, I was a little lost because I thought you did the math in your head instead of in the calculator.
No, trust me, I could not do that in my head. Okay. Yeah.
Okay, got it. Thank you.
All right. You betcha. Okay, let's see here. We're going to go on to another student's work here. And question. Let's see. Here we go. This is also from 11.4. This is number 23. Okay. All right. So this is 11.4, number 23. It says solve for x. And we have the logarithmic equation, log base x of 0.01 equals -2. All right. So this is a logarithmic equation. To solve it, I'm going to transfer it into, or change it into, an exponential equation. So that would be x to the -2 power equals 0.01. Are we okay with that? All right. Now, yesterday we talked about if I have something like a squared equals b to the box, that if the base, well, actually, if a squared equals a to the box. So if the bases are the same, then the exponents would be the same. Likewise, if we have the exponents the same, we can get to the bases being the same. Now, how am I going to do that? How could I take this and write it to something to the -2 power? Well, isn't 0.01, isn't that 1/100th? Which would be 1/10 squared, which would be 10 to the -2 power. You see how I got from here to here to here to here? So x is 10. That one was a little bit tricky. We okay with this? Okay, we're going to go on then. This is also in 11.4. This is number 33. It says evaluate the logarithmic expression. Log base 1/9 of 1 over 729. So I'm supposed to evaluate this expression. Well, I'm going to say that it's equal to some unknown box. Okay. So if I were to rewrite this as an exponential equation, I'd have 1/9 raised to the box power equals 1 over 729. 729. Let's see what that is. 729. In fact, I'm suspicious. Is there a 9 in that? So I'm going to go 729 divided by 9 is 81. Oh, so this is 9 times 81, which is 9 times 9 times 9, which would be what, 9 cubed? So 729 is 9 cubed. Okay, well, where does that get us? That gets us here. Okay. Now, what's 1 squared? It's 1. What's 1 cubed? It's 1. What's 1 to the 4th power? It's 1. What's 1 to the 5th power? It's 1, right? So could I also make that, and ultimately make it that? Since 1 is equal to 1 cubed, and now I've got 1/9 to the some unknown box power equals 1/9 cubed. So what does the box equal? 3. Again, kind of tricky. So the idea is, can you get this to match, or this to match this, so that that matches that? It's like working puzzles. Okay, we've got one more set of questions here. Let's see here. This is here. And here. Okay. All right. This is still in section 11.4, and this is number 9. It says, write the logarithmic equation as an exponential equation. We have n equals log base b of r sub 1. So the base is b, so b to the n power equals r sub 1. Any questions about that? And then number 33, 11.4, number 33, it says, evaluate the logarithmic expression. We have log base 1/2 of 1/8. So that's equal to some unknown. Changing this logarithmic equation into an exponential equation, we get 1/2 to the box power equals 1/8. But 8 is 2 times 2 times 2, or 2 cubed. So 1/2 to the box power equals 1 over 2 cubed, which is equal to 1 cubed over 2 cubed, or 1/2 cubed. So 1/2 to the box power equals 1/2 cubed. So the box equals 3. So the answer is 3. Okay, well, those were the questions that came in yesterday through email. Do you have any other questions before we go on to the next section?
Yes, I had a question on number 2. For some reason, this is one I struggled with the most. I could not figure it out.
Okay, just a minute here. Let me find, let's see. 11.4, number 2, come on. Okay, is this the fill in the blank?
Yeah, it is a fill in the blank.
Okay, so it says, part A, log of x equals log Oh, I see what they're doing. Okay. So basically, this first part is about understanding that if there's no base written, it's log base 10. Okay.
Oh,
That makes sense?
yeah, got it.
Okay.
I don't know why I was so confused, but thank you.
Yeah, no, I can see it's a little confusing, the notation there. We're not exactly sure what they want. Okay, any other questions before we go on? All right, so we're going to go on to, whoops, 11.5, and we'll close that up. And now we've looked at log base 10, and we said that base 10 was commonly used in logarithms, therefore it's called common log, and it's used so much that we just write it as log. We don't even bother to put the base. There is another very popular base, and that isn't 10, it's the number e. Now, e looks like a variable because it's a letter representing it, but it's not. It represents an irrational number. It's kind of like pi, in that pi relates to things like circles or spheres, diameters, circumferences, not diameters, but circumference of a sphere, or the volume of a circle, or wait, I got that backwards. Anyway, the volume of a sphere or the area of a circle. Anytime you're dealing with something that's got a circle involved, pi, which is approximately 3.14159 and just keeps going and going, is used in that situation. And we often write pi as 3.14. Okay, now e is used whenever you've got something that is growing or decaying continuously. Okay, now let's look at an example. In the state of, well, let's just take the city of Yakima. Is this the way that things work? Starting on January 1st up until December 30th, nobody's born, nobody dies, and suddenly on December 31st, a bunch of people are born and a bunch of people die and the population changes. Is that how it works? Is it just sort of nothing and then all of a sudden, boom, there's a big change? No, the population is continuously growing or decaying. If you look in the newspaper, every day there's death announcements, there's birth announcements, okay? So it's a continuous process. Now, let's take that in terms of money. We looked at an equation yesterday, or a formula that was for computing compound interest. And we had how many times that interest was compounded. Yearly would be once, semi-annually twice, quarterly 4 times, monthly 12 times, daily 365 times. What if it was compounded continuously? So again, the idea that it was growing continuously. Then we use E in that formula. Now, what exactly is E? Or what number does it represent? Well, E is approximately 2.71828, let's see, 459, and then it goes on and on and on. Okay, so let's just roughly approximate it and say this. Let's say that it's a little bit, it's about 2.7. Okay, so E is slightly less than 3. Pi is slightly more than 3. But we use E whenever we're dealing with something that's growing or decaying continuously. All right. Now, let's see here. Oh, log base E is commonly used just like log base 10. But since they've already got log base 10, just writing it as log, they wanted some other shortcut notation. So they decided that log base E was going to be the natural log, and they were going to write it ln. Okay, So 2 shortcut notations. This one from yesterday, log base 10 is written log, and log base e is written ln. Now, if you have your calculator handy and you look at it, you'll see that over on the left column, there's the button log, like we talked about yesterday, and the second function key is 10 to the x. Right below it, there's a button that says ln, and its second function key is e to the x. So the 10 to the x reminds you that log base 10 is log, and the e to the x reminds you that log base e is ln, or ln. Okay, so we have to get used to that shortcut notation. All right, now we're going to do some of the same things we did yesterday. And let's see here. I'm going to switch screens. So give me a second. I'm going to get rid of that and go here. Maybe. Okay. And okay, let's take a look at that screen. Now, we graphed something like y equals 2 to the x, and y equals 3 to the x, and y equals 1/2 to the x. We did that yesterday. Now we're going to graph y equals e to the x. Since e is slightly less than 3, the graph should look very similar to y equals 3 to the x. But I'm just going to go ahead and make a table of values like I did yesterday. And again, I'm going to use -3 to +3 as x values to put in. Now, when x is -3, y equals e to the -3 power. How am I going to do that on my calculator? Well, remember that button that's e to the x? That's the second function key of ln. So you're going to push the second function key, okay? And then you're going to push the ln button, which is then going to access, let's see here. It's going to access e to the something power, okay? Then you're going to put -3 in there, close it up, and I'm coming up with 0.049787, etc., etc. I'm going to round that off to 0.05. Okay, is anybody using their calculator right now and they're not getting this answer? If so, let me know and we'll walk through it again. Okay, so now I'm going to do the same thing, except my exponent's going to be -2. And I get 0.1353, etc. I'm going to write 0.13. And then let's see here, we'll put in -1. And I get 0.3.
Wouldn't it be?
What?
For -2, wouldn't it round to, for -2, wouldn't it round to 0.14?
You are so correct. Good job. I was so focused on other things that I messed that up. Thank you. Thank you very much. Okay, so this is going to be, yeah, this is going to be a 4. Excellent. Okay, so likewise, what's 0.367 going to round to? To the 100th place. It'd be 0.37, wouldn't it? But for the same reason there. In other words,
Yes.
okay. All right. And then, oh, what's e to the 0 power? You don't need your calculator for this. It's 1. Remember, anything other than 0 to the 0 power is 1. Okay. And then e to the 1 power would be 2.7. And I know I'm not being consistent in my rounding here. It's because I'm just going to get an approximation. I'm not going to be able to graph this thing accurately as the numbers are anyway. Okay, so let's see. E to the 2 power is 7.38. I'm going to make that 7.4, and E cubed is 20.08, so we'll say 20.1. And I know I rounded to the nearest hundredth at the top and then to the 10th down below. Very inconsistent of me, but what's the graph going to look like? Well, let's see. When x is -3, y is 0.05. So that's like right almost on the x-axis. Okay. X is -2. We go to 0.14. Let's see, 0.14, that's about 1/7. So again, that's probably right about there. At -1, we're up to 1/3. I can see already that my graph is not super accurate there. 0 at 1, 1 is 2.7, 2 is 7.4, and 3 is off the graph. Okay. So my graph looks kind of like that. Can you see this? Yeah, you can. Okay, here's what I'm going to do. Just to show you. Let's see here. This is the graph of 2 to the x power. Okay. Now, here comes the graph of 3 to the x power. So that was that second one. And now let's put in e to the x power. See how it's really close to 3 to the x power there? I don't know if that shows up very well. Anyway, okay. My point in all of this, e is a number. It's slightly less than 3. Treat it like a number, not like a variable. When do we use it? We use it with exponential growth and decay problems. Okay. All the shifts and flips and everything that applied before are the same. If I graphed y equals e to the, or negative e to the x, that would flip this thing over. Y equals e to the x plus 4 would move it up 4 units. Y equals e to the x plus 4, where the plus 4 is part of the exponent, would move it to the left 4 units. So all those things that applied going all the way back to parabolas, and then yesterday with exponential graphs, they all apply when e is a base as well. It's just like graphing 2 to the x or 3 to the x, same kinds of things. Okay, now what I want to do next is I want to go back to my other screen. And let me make sure that you are seeing what I want you to. So now you see the whiteboard again. Okay. The formula for compound interest that we looked at was A equals P times 1 plus R over K to the KT power. And we did some problems with that yesterday. Okay. Now we're going to use a formula involving where something is compounded continuously. And what it looks like is this: A equals P times E to the RT power. So it almost has the word pert there. Does anybody use pert shampoo? Is it so around? Well, anyway, A equals P times E to the RT power. So RT is the exponent on E. It says find A using the formula A equals PE to the RT, given the following values of P, R, and T. Round to the nearest hundredth. All right, so P is going to be 5,000. R is going to be 8%, and T is going to be 20 years. Now, we need to convert the percent into a decimal. So 8%, 8 per 100, 0.08. So, and let's see, so A equals 5,000. That's P, we're not using this one anymore. E raised to the power 0.08 times 20. That's supposed to be a little multiplication symbol there. Okay, now I can put this all into my calculator just like it is, or I can predetermine 0.08 times 20 and use that as my exponent. I'm just going to leave it as it is. So I'm going to go 5,000. Okay, so on my calculator, 5,000. Then I've got to go second ln, which gives me e to the power. And then inside 0.08 times 20, close it up. So 0.08 times 20, close it up, equals, and I get 24765 point, and it said to the nearest hundredth, 162. So the 6 would round down, so we get 24765.16. All right. Any questions about that problem? Okay, let's take a look at another example. Again, we're going to use the formula A equals PE to the RT. Now we're going to see, let's see, okay, P is 15,895. R is negative 2%, so that would be negative 0.02. And T is 16 years. Again, round to the nearest hundredth. So A equals 15,895 e to the negative 0.02 times 16, close it up, equals. Okay. 15,895, second ln, so I get e to the parentheses, negative 0.02 times 16, close it up, 11,552.13894, rounding to the hundredth, the 8 would round up, so we get 11,542.14. Any questions on that? Okay. Next, it says, evaluate each expression without using a calculator. So we've got the natural log of e to the 5th power. Okay, so I want to evaluate that. That's equal to some unknown value that I'm going to just call box for the time being. Keep in mind, ln is log base e. So I've got log base e of e to the 5th power equals box. So all of this, oops, let's go back to it. All of this is all of that. And then the e to the 5th is the thing we're taking the log of. Okay, so log base e of e to the 5th equals box. If we take that logarithmic equation and write it in exponential form, we get e to the box equals e to the 5th power. So the box is 5. So the natural log of e to the 5th power is 5. Questions on that? All right, how about this one? The natural log of 1 over e cubed. Well, that's equal to some unknown box. ln is log base e. So I've got log base e of 1 over e cubed equals the unknown box. Change this to an exponential equation. E to the box equals 1 over e cubed. Well, 1 over e cubed could be written as e to the negative 3 power. So the box is negative 3. Now, we're doing something here that we don't usually do. We don't usually take something that has a positive exponent and rewrite it as an expression with a negative exponent. Usually we're going the other way around. But for our purposes here, we're trying to match this form, not this form. So we're forced to turn it into a base with a negative exponent. Okay, so a different idea than we've used it for in the past. Okay, how about this one? Let's see. The natural log of the fourth root of e cubed. That's equal to some unknown box. Natural log is log base e. So I've got the log base e of the fourth root of e cubed equals box. So e to the box equals the fourth root of e cubed. Let's go back to chapter 9. Isn't that e cubed to the 1/4 power, which is e to the 3/4 power? My box keeps getting more and more distorted. So the box would be 3/4. So the natural log of the fourth root of e cubed equals 3/4. Okay. Then it says use a calculator to evaluate each expression. So let's take the natural log of 35.15. So now we're just going to push that ln button, not the second function key. We don't want e to the x, we want the ln button. So natural log, and it shows up like that. Then I'm going to punch in 35.15, close it up, and I get 3.559624618. And it's said to do what? Round to 4 decimal places, which would be right there. The 2 would round down, so we get 3.5596. Okay, let's see here. Let's do this. Let's take the natural log of -10. ln -10. Oh. I got it said non-real or domain error. Now yesterday we talked about how the base of the log had to be positive and not equal to 1. Well, let's talk about the thing you're taking the log of. Let's say I've got y equals b to the x. Okay, so we're going back to an exponential equation or form. B has to be greater than 0, and b can't equal 1. What's the domain? Well, the domain could be, let's see, any real number, right? Because if we graph this thing, domain is any real number. But what about the range? The range had to be what? Greater than 0? Do you remember all this? This is going back a couple days ago. So when it's as an exponential equation, the base has to be positive but not equal to 1. The exponent can be any real number, but the result has to be greater than 0. So if we take this and we write it in this form, remember this has to be greater than 0, so this has to be greater than 0. That means the thing we take the log of has to be greater than 0. So when we've got an expression like this, b has to be greater than 0 and not equal to 1. X can be any real number, so we can get a positive or a negative answer. But y, this thing we're taking the base of, has to be greater than 0. So that's why way back here, when we took the natural log of -10, I think on a scientific calculator, it says something like domain error, okay? But you can't do it. All right, anyway. It says solve each equation, express all answers to 4 decimal places. The natural log of x equals 1.4023. Well, again, natural log is log base E. So ln is the same thing as log base E. So now taking that logarithmic equation and writing it in exponential form, we'd get e to the 1.4023 equals x. So on my calculator, I'm going to go second function ln, so I get e to the, and then I'm going to put in the 1.4023, close it up, and I get 4.064537661, but it said round to 4 decimal places, the 3 would round down, so x would equal 4.0645. All righty, let's do one more of those. Let's say we've got the natural log of x equals negative 0.28. That's the same thing as log base e of x equals negative 0.28. So e to the negative negative 0.28 equals x. So on our calculator, let's see here, e to the negative 0.28, and we get 0.75578. The 8's going to round up, so 0.7558. Let's see. Okay, so that's it for today. Tomorrow we'll continue in this section with some application problems. But again, don't forget, log means log base 10, ln means log base E. And I'll stop the recording.